Hello and welcome. Let's talk about bitwise operators. We showed you a little glimpse of this in the previous lecture when we talked about assignment operators, because assignment operators have all these compound assignments where you can perform an operation, like an addition, and then also assign. You can do the same things with these type of operators. But let's go into these in more detail and exactly tell you what they are. So C offers bitwise logical operators and shift operators. Those terms might be completely clueless on. They look like logical operators, but they're quite different. They don't do any kind of Boolean evaluations. They don't evaluate to true or false. They're not. They kind of look like the ampersand, the two ors, but they're not doing any kind of Boolean evaluation. What they're doing is they're operating on bits inside integer values. And so you may ask yourself, why the heck would you ever want to do this? Well, it's not used in most programs. It's more of an advanced technique. Even though this is a beginner class, they are part of the operators, and operators are a beginner concept. So I'm going to address them, but we're going to not necessarily focus on them a ton. I'll give you some examples, show you how you can use them, but you're not going to be an expert in this after this lecture. But the way that they're useful and why you'd actually want to use them is because you can store quite a bit of data. So there's bitwise operands called and, ampersand, and the bitwise or, which is an or, just a single parallel bar. Try not to get these confused again with the logical operators. The logical operators have two of them. Ampersand, which is an and. The bitwise operators just have a single. So just an ampersand or just an or. And so what they're going to do is they're going to test and they're going to set individual bits inside of an integer variable. What is a bit? Right? We know a bit is a way to measure data. But a bit is essentially just a 0 or 1 value. And 8 of those make up a byte, right? So a bit is a 0 or 1. And what you can do is an integer, remember, depending on the system you're running, could be 8 bytes. And so you could turn on and off each bit. And when I say turn on or off, I'm saying you can either have them be equal to 1 or 0. And then you can use those bits to tell you something. So you can store a lot of data by having bits represent some kind of data. And that's why one of the reasons why the computer uses bits and 1 and 0s and binary numbers to do operations, because you can store a lot of data. Now, exactly what this means is, here's an example, okay? You could use a single integer variable. Again, an integer is a number. An integer represents 4 to 8 bytes, depending on what system you're running. That means if there's 4 bytes, that means there's 32 bits. There's 32 zeros or 1 values. All right, so you can use all those bits to represent something. So, for example, if you want to store individual characters of a person, you could just have 1 bit tell you whether or not the person is male or female by saying 1 is equal to male, 0 is equal to female. You just either turn it on or turn it off. Then you could use 3 bits to specify whether the person can speak French, German, or Italian. So the 1 bit could represent French. If it's not 1, 0, then that means they don't speak French. If German is 0, that means they don't speak German. If it's 1, it means they do speak German. So by turning off and on these bits, setting them 1 to 0, you can represent a lot of data. You could have another bit to record whether the person's salary is $50,000 or more. If it's 1, it's true. Yes, it is. 0, false. So basically, we just specified here, it actually says 4, but we actually specified 5 bits of data. Only 5 out of whether or not we have 32 or if we have 64 bits, but we only used 5 and we were able to represent whether or not a person is female or male, whether or not they speak French, German, or Italian, or all 3, or one or the other, and whether or not they're making more than $50,000. We can represent all that data in our bits. And these is where the bitwise operators come in handy. Now that we know how we can use bits to store a lot of different data, let's talk about those binary numbers. We know that a binary number is just a number that includes 1s and 0s, and that's why it's advantageous to use bit operators in an integer. The number can be of any length. The following are examples of binary numbers, right? Just 0s and 1s. So you've seen this: 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. And remember that a byte is 8 bits. An integer is usually 4 bytes on most platforms. It depends on the architecture, but mostly 32 bits. So you have 32 values that you can store with 1s and 0s to indicate on or off. Binary numbers, again, every binary number has a corresponding decimal value, so you need to understand how to convert binary to decimal. examples here. 1 is equal to 1, 1 0 is 2, 1 1 is 3. These are simple conversions. Again, usually they have more bits. 1 0 1 0 1 1 1. The way that you want to convert the binaries numbers to a decimal number is you want to look at each position in the byte with the bit, corresponding bit, and then use the power of 2. So for each digit, you multiply the digit by its position value using the power of 2, and then you add up the entire project to get the final result. So position values in a binary number are the powers of 2. So the first position would be the value 2, 0, which in other words would be 1. All right. And then the second position would be the value of 2 to the first power, which is 2. 2 to the 2 would be 4. 2 to the 3 would be 8. 2 to the 4 would be 16. And you keep doing that over and over again. And so it's easier to understand if you see a nice example. And so here we have a binary number of 011 01 001. The decimal equivalent of that is 105. The way that you convert it is you start on the right-hand side for each bit, and you multiply to the power of 2 depending on if the bit is 0 or 1. So if we start all the way to the right, we have 1, so we say 1 times 1, and we keep that 1. Then the next one, the second position, is 0 times 2, 0. And then 0 times 4, 1 times 8, 0 times 16, 1 times 32, 1 times 64, and 0 times 28. And you add all those up, and you get the result of 105. That's one way to convert it. You can actually convert it left to right as well by multiplying by 2 and then adding 1 or adding 0 depending on what the next bit is. So for example, you can also, if you go left to right, you can say you start off with 1 because 0 doesn't matter. So the second bit going from the left to right, you have 1. The third bit you have 1 times 2 plus 1, so you have 3. Then again, you multiply by 2, so you say 3 times 2 plus 0, which is 6. 6 times 2 plus 1, which is 13. 13 times 2 is 26. 26 times 2 is 52 times 2, which is 104 plus 1. So again, multiply by 2 and then add 1. Another example, again, the right to left is usually a little bit easier. Here's 100111100. And that converts to 156 because you say, again, 0 times 1, 0 times 2, 1 times 4, 1 times 8, 1 times 16, and so forth. And then you add all of them together, which is 4, 8, 12, 16, 28 plus 128 is 156. And again, if you go left to right, you multiply by 2, add 1. So we start off at 1, say 1, 2, 4, 9, 4 times 2 plus 1, 9 times 2 is 18 plus 1 is 19 times 2. 38 plus 1 is 39 times 2, which is 78 times 2, which is 156. So this is a quick demonstration of how you can convert binary to decimal. Now, converting decimal to binary, I usually just use a conversion on the web if you're really interested in that. But you can take these binary numbers and then perform bitwise operators. So let's take a look at the bitwise operators. So the bitwise operators are summarized here. And again, another nice table I got online, but they look similar to logical operators, but again, don't confuse them. So the ampersand by itself is a binary AND operator. And so what this is doing is it's copying a bit to the result if it exists in both operands. So if both of them are true, then it's going to copy a bit. So if A and B is equal to 12, you're going to have a binary representation of 00001100. So A and B would be that number. And we'll go through some examples. A binary OR copies a bit if it exists in either operand. Okay, so A or B will copy a bit if it exists in either operand. So if either operand is equal to 1, it will copy a bit. And then the binary XOR, this is the exclusive OR. This will copy the bit if it is set in one operand but not both. So if you have a true but only one true, and you use the caret to represent this on your keyboard, then it's going to set, it's going to copy a bit and it's going to say it's true. Binary one's complement. So again, we're getting the binary data here because we're talking about bits. So hopefully one's complement operator is unary and has the effect of flipping the bits, basically just negating them, taking the amount off. So an example here was if you say tilde A, you're applying the ones complement operator. And if it's equal to negative 61, it will be 1100001, right? So if you were to actually convert that binary number to decimal, which is negative number, and the first number is the sign. So 1 tells you that it's a sign, and then you say 1, 2, 4, 8, 16, 33, 33, and then 61. So that's how it would be represented. So I'll go through more concrete examples of this, but basically, if you have a binary number, A is initially a binary number that's 00111100, which is 60, and you supply the flipping, basically, it's going to then turn into negative 61, which is 110000000011. Right? So these are the results of variables that are actually set. So if, again, I'm assuming that A has certain binary representation and B has a certain binary representation. So if A is equal to, again, 60 and B is equal to 13, then the result of ANDing them together, doing a bitwise AND, is going to be 00001100, which is 12. Again, I'll go through these examples, but this is trying to provide a little description of these different binary operators. The greater than symbol is going to, the less than symbol is going to shift bits to the left. So the left operand value is moved left by the number of bits specified by the right operand. So if you do something like A less than 2, and A is actually equal to, some binary number, for example, like 00111100, you're going to shift the bytes by 2. So you're going to take off the zeros, and it's going to become 1111, and those zeros are going to go to the end. And the same with the right shift operator. You're just shifting them to the right as opposed to the left. Here you use the greater than symbols. And so I'm going to go through these in a second. The other important thing to understand with the bitwise operators is how do you evaluate these A and B values, right? So what does a 1 and a 1 evaluate to? A 1, if it's an ampersand. If it's an OR, 1 and a 1 evaluates to a 1 as well. But a 1 and a 0, if you're using an ampersand, doing an AND, that evaluates to 0, false, right? So I just wanted to provide a little truth table here that shows you the values when you use an AND, an OR an exclusive OR. So here, if you have P0 and Q0, which means they're both false, and you apply an AND, it's going to be false because they both have to be true for that to be true. And that's what you see in row 3. If they're both true, then P and Q is going to be evaluated to 1, true. If they're not both true, it's always false. P or Q, only one of them needs to be true. So that's why you see rows 1 and rows 2 equal to 1 and row 3 equal to 1. The only time it's false is when they're both false. And then the exclusive OR is at least one of them is true and only one. Right? So if P is false and Q is true, it will return 1, true. And if P is true and Q is false, it will return 1. So this gives you an idea of how it's evaluated. Again, a lot of math stuff, but when we talk about binary digits, that's what we're talking about. So let's look at some examples, concrete examples in code blocks. Hopefully this will help a bit. Okay, so here's our function. I'm going to create a couple more variables. I'm going to make sure that they're unsigned, even though that's by default. So if I say unsigned int A and assign it to 60, that's actually going to be represented in binary as 0011 and then 1100. If I create another unsigned variable and I say int B and I assign that the value of 13, that's going to actually be represented as in binary as 00001101. You can do the conversions there. But what I want to demonstrate here is that when you set these binary numbers up, you can turn off the bits by using the different bitwise operands. Okay, so now then I'm going to just create a int result, and I'm going to say that's going to be equal to 0. He's going to hold the result of the bitwise operation. So now if I say C equals A and I apply the bitwise amperand and A and B, now what that should do is if A is equal to 1 and B is equal to 1, that bit's going to be turned on. Right? So what would you expect the result of this be? Well, you look at the first bit of A and you look at the first bit of B, and they're both 0. So the result is going to be 0, because if you do a true, an A and a B, they both have to be true in order to be 1. So the next one is also going to be 0. The next one is 1 and 0, the third bit. So that's still 0, 1 and 0, still 0. And then now we have a 1 and a 1. So now we finally have a true. We have another 1 and a 1. We have a true. And then 0 and 0 is going to be 0. And then a 0 and 1 is going to be 0. So the result, if I were to try to print out C, it's going to print out the value in decimal format. If I were to do something like that, the result is it's going to print out the decimal equivalent of that binary number, which would be the equivalent of 0, 0, 0, 0. And this is all converting binary to decimal, so you need to understand how to do that to understand this example. But 0, 0, 0, 0, 1, 1, 0, 0 is actually 1, 3, 7. That's the value is actually is 12. 1, 3, 6, 12. So this would print out 12. Right? If I were to print out C, or result would be better. So if I run this, you're going to see that the value is 12. It actually turned off and on all the bits based on the ampersand comparison. So now I say run. We see that the value is indeed 12. Because it's turning off and on the bits, and it's going to actually be represented as 0, 0, 0, 1, 1, 0, 0, which is the value 12, because we're printing out its decimal. If I were to change this, and I want to now do an OR, and I'm still doing the OR, and the OR, remember, is the parallel bar right next to the enter. Now I'm only going to turn on bits if either one is true. So 0, 0, both of those are false. Again, I'm comparing up here, right? I'm comparing these bits for 60 and 13. 60 is represented as binary 0, 0, 1, 1, 1, 1, 0, 0. 13 is represented as binary 0, 0, 0, 0, 1, 1, 0, 1. Each one of those numbers represents a bit. So the first bit in 60 is 0. The first bit in 13 is 0. And if I OR those together, 0 and 0, I'm still going to get 0. So that's the first result of the first bit. Second bit, 0, 0 again. Third bit is 1 for 60, and it's 0 for 13. Now, all that means is I have to have 1 true, so that's going to be a 1. Same goes for bit number 4 in 16, 13, so now I have a 1 again. And then a 1 and a 1, they're both true. So again, 1. All I need is 1 true. Another 1. Both false, so that's not going to be true. 0, remember, is not true. 1 is true. And 0, 1, 1. So now I have 0, 0, 1, 1, 1, 1, 0, 1. And the value of that in decimal, if I were to print it out, is again, you have to understand how to convert binary to decimal, but it basically goes 1, 3, I'm trying to add these up, these bits as I go, 1, 3, 7, 15, 30, 61. So this is going to print out 61. Oops. End this program and rebuild it, and we're going to see a value of 61. And we do. So that's bitwise operators. And again, it's a more kind of advanced for advanced programs, but it's a nice way to represent a lot of data by using ampersands and so forth. By turning on and turning off bits, essentially. So if you didn't, you could play around with this. You could do the exclusive OR, which is the caret, right? The caret is above the 6, number 6 on the keyboard. You would see a different result. If you would add the tilde, that's just going to basically turn everything off. So for A, and A is equal to 60, 0, 0, 1, 1, 1, 1, 0, 0, it's now going to be equal to 1, 1, 0, 0, 0, 0, 1, 1. Another really cool thing you can do with the binary operators is shifting, right? Shifting left and right. There's a couple key things you know when you need to shift left or right. First of all, we know that an unsigned int means that can only be positive. It can't be negative. So if you're storing a negative value in there, the compiler will convert it and it'll be longer, it'll take up a lot of size. So remember, unsigned ints mean that you can only have positive values. Signed integers mean that they can be unsigned or negative or positive. But if you want to shift, remember, in order to shift to the left, so now if we say result equals, and let's say we want to shift A, let's say by 2, right? The other important thing you want to know is when you have the integers, integers are, remember, they're 4 bytes on most platforms. It depends. You can get the size by doing the size of operator. So really, the integer is really 32 bits. So really the number is something like this 16, something like that. What is that? 4, 8, 12, 16, 20, 24. So you probably do something like that and something like that, right? That's really the number. I only showed the last 8 bits because the rest were zeros. But if you look at this as a 32-bit integer, which is 4 bytes, this is what it looks like in binary. 4 zeros, 4 zeros, 4 zeros, 4 zeros, 4 zeros, 4 zeros, and then the 0, 0, 1, 1, 1, 1, 0, 0. And so you kind of got to know the size when you do the shifting to left to right, because if you shift more than 2, it's not going to be clear. You don't have any, it doesn't drop off or anything like that. So again, let me just make sure 4, 8, 12, 16, 20, 24, 28, 32, right? And the same would go for 13. So if you were to shift to the left, a greater than 2, what you're end up going to have is these ones are going to shift to the left too. So what the result is going to be, still all those preceding zeros, but then you're going to have 1, 1, 1, 1, 0, 0, 0, 0, right? And that is going to be equal to 240, right? And if I do a quick conversion, I do it in my head by saying 1, 3, 7, 15, 30, 60, 120, 240. But we can confirm that by building and running. I want to make sure we spell this unsigned correctly. And you'll see that the result is 240. And we see the result is 240. All right, so now if you want to actually shift to by more than 2, say you want to shift by 4, this is when it becomes important to understand that it's a 32-bit number. Right? So here you would actually have to use some of those zeros. So if you want to shift by 4, really what you would have is you would just have something like that. And then, if you want to group them by 4, you'd have something like, like that. Right? And so the result here would be, again, if I do this in my head, you have 1, 3, 7, 15, 30, 60, 120, 240, 480, and then 960. Hopefully I did that right. Again, when we run this and we say 960. So that's shifting to the left. If you want to shift to the right, use the greater than symbols. So shifting to the right, binary right shift operator, you do the greater than. Binary left shift operator, you do the less than. So here, if you're going to shift to the right, you want to move to the right 4. And what happens if you have the end here, so if you have your original 60, you try to go 4, you're going to have digits that just get dropped off, right? So instead of having, these last 4, which originally, again, we have 60, so we have 0, 0, 0, 1, 1, 1, 1, 0, 0, we have to move over 4. So we're going to end up losing 2 bits because they're just going to drop off, and what we're going to end up with is something like this, 0, 0. And so this would just be equal to 3. Something like that. So you actually lose bits because you're shifting to the right too much. Let's see if we can run this. And you have the result of 3. So you have to be careful when you shift left and to the right. Make sure you use those 32-bit bits, 4 bytes, again, depending on your system. It's a quick summary of bitwise operators. You would also need to, when you get more advanced, you'd have to understand how you can actually check if a particular bit is 1 or 0. It's pretty simple. You just do an AND on it, but you do have to write a little bit more code. This lecture was not intended to be an exhaustive look at bitwise operators. I wanted to give you an overview, give you a good head start on it, but in order to understand these operators more, you're going to have to study quite a bit more and use them and practice them. So I hope this was helpful. Again, it can get a little confusing, so you want to follow and you want to play around with it. But again, what's the best way to learn? Write some code, learn some examples. Thank you.